matter into two categories. So think about what those two categories might be. So I don't steer in the headlights well. Ready? Yeah, don't start filming now. Hurry. Pressure.
I'm still trying to test it.
Wobble your ring stand for a minute. And this will cover the hair, which people call this bad hair burning smell. Okay, ready? Make it go. Is it going? Bad hair burn smell. That's awesome. Okay, so we can split matter, which is everything that has mass and takes up space, into two broad and general categories. Anyone remember two categories, Micah?
Pure substance and mixture.
Pure substance and mixture. So. All right, so we've got pure substances and we've got mixture. So two broad categories we first separate matter into. So then we can break each of these categories down to more fully describe them. And we can break those into two categories each also. So pure substances are what? Elements and compounds. So. All right, so we've got elements, we've got compounds. So what is an element?
A single atom.
Okay, a single type of atom.
Yeah.
So if you can find it just like it is on the periodic table, it's an element. The periodic table of the elements. So if it's on here, it's an element. It is a substance composed of one type of atom, one type of nucleus element. If it's one type of nucleus in the substance and it's found on the periodic table, it is an element. How about compounds? Kristen, what's a compound? Okay. So, or, I mean, you can have, well, our homonuclear diatomics are elements. Maybe I'll put that here. Even though they are a molecule, they still are the same kind of nucleus bonded together, so they're elements. But here compounds are, tell me again. Okay. And those two or more elements in the molecule have to be attached how? And ionics are a little different. You haven't learned quite enough yet. I can't remember when I get to teach you why that's not, chemical bonds aren't exactly right for ionics. They're held together by electrostatic bonds. But you'll get that later. But compounds are made of molecules with two or more elements held together with some kind of bond. For covalence, it's a chemical bond. For ionics, it's an electrostatic bond. But you don't have to get any more detailed than that for now. And how can you identify a compound if somebody shows you a list of stuff. How could you pick out a compound from an element or mixture?
Based on its chemical formula?
Okay, so it has a chemical formula. You can always write a compound down as a chemical formula. So that's the key on this test to identifying compounds. Okay, so if I write a few things up in the corner here, like alright, so I've written 4 things up here. They're all 4 pure substances. They're either an element or a compound. How could I figure out which? So titanium, Ti.
Element.
It's an element. How do you know?
Well, first of all, it's by itself. There's no other atoms to be joined with.
Okay, so one type of nucleus and
It's on the periodic table.
on the periodic table. So slow at finding right here. So if it's on the periodic table and has one type of nucleus, it is an element. How about O2? Lily?
The compound.
Is it? That's where it's tricky. So, right, it is a molecule, so that's why, you know, we have to be careful. But it's one type of nucleus. It's a homonuclear diatomic. So it's oxygen on the periodic table, one type of nucleus. So this is actually an element. CO2? That's a compound. 2 types of nucleus. Is it ionic or covalent?
Covalent.
It's covalent because they're both nonmetals. Carbon and oxygen are both nonmetals. So covalent held together by chemical bonds. So it is a compound, pure substance, written with a chemical formula, 2 types of nuclei. How about magnesium sulfate, which you guys don't know how to name yet, that's fine. But you can see its chemical formula here.
Compound.
Compound. This one's ionic because magnesium's a metal, sulfur and oxygen are both nonmetals. So you have a metal and some nonmetals, that's ionic. So it's a compound, it has a chemical formula. But then there's this whole other category of matter, mixtures. So, oh, I didn't do color. Yep, got enough colors. Oh, here we go. Somebody switched all the lids and confused me. So, we have 2 types of mixtures also. Alright, so Grace.
Heterogeneous and homogeneous.
Okay, so 2 types of mixtures. We've got heterogeneous and we've got homogeneous. Alright, so if you look at your roots here, hetero means Micah? Different. And homo means same. Okay, so a heterogeneous mixture is
Something where if you look at it at different points, it can look different.
Yeah.
excellent. So different composition at different points. And a homogeneous mixture
Is the same everywhere.
same everywhere. So if I take a sample from, let's say I had a cup of water here, well, I probably, here, tiny bit of water. So, this water is not looking very homogeneous. But if this were just water, distilled water, if I took a sample from this side and then that side and deep down in the bottom and up near the top, would I find the sample to be consistently the same throughout? Yes. Well, of course, water is a compound, H2O. What if I then looked at my tea? Let's pretend the ice is all melted first, and then we've just got tea. So if I have tea with sugar in it, would that be element, compound, heterogeneous, or homogeneous mixture? Lily?
Be a homogeneous mixture.
Homogeneous mixture. And so the reason for that, okay, well, what we have in tea without the ice is water, liquid, with sugar dissolved in it and tea dissolved in it. So those things, when something is fully dissolved, like sugar and tea fully dissolved in water, they spread themselves evenly because of the random motion of the molecules. They make a homogeneous mixture. Now my tea, you can hear, has ice in it still. So if I took a sample from down deep and a sample from up at the top, might I get a different thing from a different part of the mixture? So this particular cup of tea is a heterogeneous mixture because the ice isn't completely evenly dispersed throughout. It's floating here at the top. There are little chunks, big chunks. Maybe it's diluting the top a little more than the bottom. So tea with ice would be a heterogeneous mixture. Just sugar water with tea would be a homogeneous mixture. Right here, I have kind of a more complicated mixture. So first, let's consider there's an egg in here. So my egg, is it element, compound, heterogeneous, or homogeneous?
Heterogeneous.
So my egg is a heterogeneous mixture. Why?
Because it's got the yolk in it, so if you looked at it, like, in a part with the white and then with the part in the yolk, it would be different.
Right, and the shell. So you've got the shell area, you've got the white area, you've got the yolk area, all kinds of other little tiny bits here and there that make up the egg. So you have different composition throughout. So the egg is a heterogeneous mixture. You can sample something yellow, something crunchy, something white, here and there. So an egg is a heterogeneous mixture. When you take the test, we'll stop here and comment about the test. There's a question that asks you what are the 4 classifications of matter or something similar to that. And that's going to be element, compound, heterogeneous mixture, homogeneous mixture. It's a very vague question. So continuous, like, I could classify matter lots of ways. I don't understand. And I'm like, okay, must tell everybody.
It's classifications of matter, or?
I will read it directly as soon as I find it. I have a test copy somewhere, probably. So, it's going to ask you, the 4 classifications that we learned for matter. That is sort of vague, I think. And then, what was the other vague question? Okay, so the next vague question is what are the 2 classifications for the changes that matter undergoes? So I'm going to label that right here. The changes matter undergoes. So,
Physical change and chemical change.
yes. So if they ask you what are the changes matter could undergo, this would be the 2. Physical change and chemical change. Chemical. Yeah.
I wasn't putting the camera,
Right.
so they missed that.
Oh, did it die?
No.
Do you need a
I
battery?
just wasn't putting the camera in. It's kind of flashing.
Can it see okay?
Yeah. But the light is flashing.
Why are we flashing? Ooh, it's really zoomed in. You don't need any help. There you go. So the changes matter undergoes. So what is a physical change?
A physical change is something that can be undone, like melting ice.
Okay, so physical change can be undone by physical means. Does it change the chemical bonds? Where are they? Does it change the chemical bonds of the substance? So physical change does not rearrange chemical bonds and can be undone. Of course, we can undo some chemical changes too, but you have to rearrange chemical bonds for that. So, I guess could be undone through physical means. So, for example, you said melting, yes? Any phase change is a physical change. So phase changes. So what are other phase changes besides melting?
Freezing,
Freezing,
condensing,
boiling. So phase changes are physical changes, boiling, things like that. How about, what did you just say, tearing up?
Tearing piece of paper.
Okay, tearing up or breaking, shattering.
Finger block.
Tearing up, breaking, any sort of tearing up or breaking. I don't know if it was a review question or a test question. I'll say this in a second. Okay, so tearing up or breaking is going to be a physical change. And the other big physical change that you'll be dealing with a lot, think of my tea. I stirred sugar into it this morning. So what happened to the sugar? Dissolving. We haven't really learned about dissolving yet. But dissolving is a physical change. So anytime something dissolves, then you've got a physical change. Now chemical changes, let's see, I'll find that. They do involve rearranging the chemical bonds. Rearrange bonds. So, what kind of chemical changes have you seen already this year?
The magnesium, like you said, the magnesium oxide.
Okay, and so magnesium combining with the oxygen from the air is a form of combustion. What else?
The lye and vinegar.
Okay, that's an acid-base reaction. How about...
Would an explosion count?
Yeah, that would be combustion.
Fire.
Chemical changes, rearranging bonds. We didn't do a lot of that until later. We're going to do some of that next week or the week after.
Yay.
Yay. What's the other thing? Oh, cooking. He uses a lot of cooking examples for chemical changes. So anytime you fry, bake, grill, any sort of cooking, you're doing a chemical change. Your food is irreparably and irreversibly changed by any type of cooking.
Wouldn't that be classified under combustion though?
What?
Cooking be classified under combustion?
No, because you're not completely reacting it with oxygen and combustion is, we'll learn in Module 5, like a very specific, like, thing you combust plus oxygen gives you carbon dioxide plus water. Like, it's always that same thing, if you're going to call it, well, complete combustion. But cooking does all kinds of other strange things, like, especially baking, you don't actually, hopefully. So, there's one kind of tricky area. Like, think if I took a package of meat out of the freezer, I put it on the counter and I thawed it out. Physical change or chemical change? Physical change, because that is just melting. Then I put the meat in the frying pan and I cook it, that is chemical change. So, those are kind of all of the tricks to the test that at least gave Jenny trouble and have troubled people in the past. So, let me see if I have more notes or if it's lab time. You guys have kinetic theory of matter today. Okay. So, pull this out and make board completely if you want to make yourself some more room. Yeah, Alright, I don't look at the bigger notebook. There's not enough notebooks in the world for this. I should split it into two, I guess, but that seems like double the chance of me losing a piece. So. Alright, so we touched just a little bit on the kinetic theory of matter when we talked about dissolving. Ooh, I should start heating something up. I tossed some tissue in here earlier because I washed these beakers here in concrete water, and it left like an actual film inside my beakers. And I didn't want to get them wet again before we used them today. But, alright, I'm going to heat up a little bit of water here, and then wipe out this beaker. I didn't notice the film until I picked them back up this week. For our purposes, this will work okay. So similar amounts of water in these two beakers, and I'm going to get one hot. And then while it heats up, we'll talk a little bit about the kinetic theory of matter. Oh, I'm completely under the thing. Okay.
I can put on my goggles.
Yeah, probably everyone, including me. Where's the goggle bag? Does everybody have a pair? Thank you for reminding me. Anyone need a pair? Good, good. Okay. So, already we're
Goggles.
You can't take the tape off just so you can use that. Daniel will cry.
Daniel's lens is slightly crazy.
He needs his eyebrows. He's waiting for me to burn mine off, maybe, I don't know. So, the kinetic theory of matter. The way I like to think of the kinetic theory of matter is CCT lunchtime, okay? So, you guys, at the beginning of lunch, you are going to flood into the gym today, all dressed up in your fancy clothes, and get pizza, right? Everyone will rush in there, right? So let's imagine that the beginning of CCT lunch is like a high energy situation here, right? You guys are excited about the pizza, your high energy, high speed molecules. If you picture you guys as unable to see and moving more randomly, you're not directional, like heading right for the pizza, right? But you're just high energy, fast molecules in motion, right? Then you would be kind of like a gas, right? High energy, fast moving, completely random motion, I guess, looking for the pizza. You're like going everywhere. And then as you get your pizza, you slow down, you become more like a liquid. The molecules move more slowly in the liquid. They get closer together, right? So gas, fast moving, far apart, very random motion. Liquid, slower moving, still kind of random motion, much closer together. And then, like once you have the pizza coma, you kind of become a solid, right? You're just vibrating in place, just locked into kind of a little grid, unable to slide around randomly anymore, but you can just vibrate there in place. So you're lower energy, closer together, because you all sit down at a bench, right? And you're all right there. So the kinetic theory of matter tells us that these three phases of matter. What in the world is that word? Particle movement. Like peptide bonds. I never teach them about that. Okay. So the three phases of matter. Gases, high energy, very fast moving. Liquids, lower energy, still moving around. And solids, lower energy and not able to move freely, just vibrating in place. So, let's see. Because, say, a solid has, well, let's talk about water a little bit. Is this hot yet? It's getting there. Okay, so let's look at some water molecules. So water is H2O. Later I'll teach you why I draw it like that and not in a straight line. And if you look here at the periodic table, you can see oxygen is far over here. I mean, if you're facing the periodic table, it's over here on the right side, and hydrogen further over there. One thing that you haven't quite learned yet, but we'll explain later, but you just need to kind of take on faith for me right now, is that oxygen attracts electrons much more than hydrogen. So when they form these chemical bonds, these are electrons here. The hydrogen has one electron that it shares with the oxygen shares one of its electrons with the hydrogen. The sharing of electrons is what makes chemical bonds. And the oxygen attracts the electrons more to itself than the hydrogen can. So it's like when siblings say, oh, we're going to buy this together with our money and then we'll share, but really the bigger sibling has all the power and like hogs the thing more. So the little sibling maybe gets it 20% of the time and the big sibling gets it 80% of the time. Oxygen is like the big sibling here. It hogs the electrons. So electrons have what kind of charge? Electrons have a negative charge. Not burning my hand off. Hold on. All right, so I'll turn that off for now. Electrons have a negative charge, so when the oxygen hogs the electron, that's a delta, probably the worst, Greek letter you would ever see. I draw them very badly. But delta is a partial charge, so this is saying a partial negative charge. The oxygen is hogging the negative electrons, causing itself to have a little bit of a negative charge. And the hydrogens don't get enough electron time because the oxygen hogs it. So they're like the little siblings. They get a little partial positive charge because they lack the electrons that the oxygen hogs. So you end up with this polar molecule, a slightly negative charge here, slightly positive charge here. And we all know that like charges repel and unlike charges attract each other, right? So when water molecules are in a liquid form, they kind of arrange themselves in space so that this little negative end gets near a positive end, like this, right? You're never going to see this partially positive end hanging out near another positive end, like this. You're never going to see that happen. The partial positives and the partial negatives repel each other. They slide around in that liquid form, just trying to arrange themselves so they get to be near their opposite charge. And they do this because this hydrogen is like, my oxygen's hogging the electrons. I can get near this other oxygen and maybe feel a little bit of glow from its electron, right? Like hanging out near a famous person, like get a little attention for yourself. So this hydrogen is just trying to get near to some other oxygen since its oxygen won't share, so it can feel some of that electron for itself because it doesn't get its fair share. So, when you have water, because it's polar, and most other liquids aren't polar, but water is, you get these little attractions. We call the attraction between one molecule's oxygen and another molecule's hydrogen, maybe I'll do this in a new color, a hydrogen bond, which you probably all learned from physical science or something. This little blue thing here is a hydrogen bond. It's not a real chemical bond. Not a real chemical bond. It's just an electrostatic attraction. Positive charge attracting a negative charge. But it has energy, right? It is another force within water. When you go to boil water, it's yet another force that you have to add energy to overcome, to break apart, so that that water can become a gas. Because gases are too far apart for hydrogen bonding to occur. That's why water is a liquid at room temperature, and most things like water aren't. Because this little extra bit of energy that you have to add to make it boil raises the boiling point above room temperature. So, now, I don't have tongs. Easy. Okay, these guys, or maybe we can see them. So I've got room temperature water, and I've got hot water, and we know that the more energy something has, the higher its temperature is. And we can pretty well guess that there's more energy in the hot water than the cold water, because we've added a whole lot of energy. So when I add this food coloring, what do you think will happen?
The food coloring will spread more quickly in the hot water than it will in the cold water.
Why?
Because the hot water molecules are moving more quickly, so the food coloring can disperse quicker.
Exactly. So I should do it like right at the same moment. Alright, so we've got an energy situation going on here. Which one will spread? So the random motion of the water molecules causes both beakers to spread the food coloring around, right? Molecules are moving constantly in liquid, crashing into other molecules. They crash into the food coloring and they move around. But you can see that the molecules, on average, in the hot water are moving much faster. So there are more collisions, more spreading, faster spreading. So we essentially have got a nearly homogeneous mixture at this point here, because it's pretty thoroughly mixed. And in this beaker, I can pick it up carefully, you can see there's still swirlies, there's some redder areas, and some areas that still look like water. And a lot of the red food coloring has sunk all the way to the bottom. Lily.
Sorry, so you said like most of it, like I can see most of it sunk, the food coloring is sunk to the bottom, but like there's still some on top. So I was just wondering like with density, like what's going on?
There is surface tension in water, and that's partly due to hydrogen bonding. And so water forms like a skin on top. You probably learned in physical science. Because at the surface, like under the water, in most parts of the water, you have the ability for every molecule to be surrounded by the opposite charge area. But at the top, there's nothing above the top layer of water. So you end up kind of getting a tighter packed layer of molecules on the surface to try to arrange themselves so that the hydrogens get a little extra electron attention from other molecules. So you do get surface tension. There are a few other causes for that, which I don't think I'm supposed to teach you about this week. But, I think I'm supposed to teach physical science stuff this week. That gets confusing. But anyhow, you can see that the random, faster motion of hot water, the more energy, moves it to a more mixed mixture. It's still not mixed, still swirly. Less swirly though, because of course every molecule still is moving, and eventually it'll probably mix itself thoroughly just from random motion. So the kinetic theory of matter says molecules move faster when they have more energy, and then water behaves a little differently because we get hydrogen bonding. Now when water starts to freeze, it's sliding around as a liquid. Oh, you can take them off for now. And then, but we'll put them back still. And then it starts to decrease in energy, decrease in temperature. It gets close to the freezing point, starts to lock into place in a solid form. These hydrogen bonds actually lock the molecules just a little further apart than they would be without hydrogen bonding, which is why ice floats, why ice is less dense than liquid water. Solid water is less dense than liquid water because the hydrogen bonds spread the molecules in the solid form apart just a little bit. Without hydrogen bonds, for most other substances, you find that the solid form is denser than the liquid form, which isn't a big surprise to most people, and it will sink. So if you take, say, plastic and melt it, and then you put solid plastic into it, that will sink, because the solid form is denser than the liquid form. If you take butter and melt it, and then you put in solid butter, it will sink, because it's a fat, and most things, fats don't hydrogen bond. Most things will, the solid will sink in its liquid form because it's denser. Water is just an exception. It's solid, floats, because hydrogen bonds make it a little less dense. Quiz next week. It says announced quiz next week on elements 21 to 40. So make sure you study for that. Make yourself a list. It says like SC, then you write scandium, and then make yourself another list that says scandium, so you can write SC. Because the quiz will have sometimes where you have to write the word and spell it correctly, and sometimes where you have the word and have to write its chemical symbol. Okay, I think I covered all the things I'm going to tell you this week. Memorize the homonuclear diatomics. I kind of pointed them out on the periodic table last week. There are 8 of them. There's 1 over here, hydrogen, and then the other 7 form a 7 right there, from nitrogen to acetine. So it's easy to memorize because it's 8 of them, hydrogen plus 7. And you'll always have your periodic table out, and you'll get used to it.
What do you mean memorize? Like memorize your name?
Just know that those 8 are homonuclear diatomics. So when if I tell you react oxygen and hydrogen to make water, you don't do this. Okay. You know oxygen and hydrogen are both homonuclear diatomics. They only exist in their diatomic form in nature. So you always, if it's hydrogen, it's H2. If it's oxygen, it's O2. But if I say carbon, it's not one of those homonuclear diatomics, it's C. It's not C2, which I've had many, many people make it somehow on the test because it's like right there next to it. Carbon's not one. So this says they're all gases in their natural form. So part of that. And where am I going with this? Oh, let's do the lab. So we probably don't need goggles quite yet until the burner goes on, and then somebody will say, hey, you think you should put on some goggles, right? Okay. All right, so a little bit more chemical terminology for you. We are going to do this lab quantitatively with respect to salt. That means we need to know the quantity of salt we're going to use. We want to measure the mass of the salt, keep track of the mass of the salt, try not to lose any mass of salt, so we have it all still at the end of the experiment. We're doing it qualitatively with respect to sand and water. We don't care what quantity of water or what quantity of sand we use. We just care about their physical and chemical properties. But we're not going to measure or keep track of the amount of sand and water. So quantitative means we are keeping track of the amount or the mass. Qualitative means we're just using it, but we're not keeping track of the amount. So when you're kind of thinking, what should I do, don't worry about amounts for sand and water, but do definitely please worry about amounts for salt. These are going to measure that. Let's look at your, oh good, my lab notes are full apart. We're going to look real quick at your lab help sheet just so I know what our goal is for the lab report here and exactly what you need to do. So this is Module 4, Day 1. No report, just turn in worksheets. So next week I think you'll have a lab report again. So make sure you've done all the corrections and studying and everything you can do this week, because you'll have a lab report. You turned in a test this week, so don't go home and take a test. You get another week on Module 4. So, I gave you a procedure, Micah.
My question, do you want us to retype up the procedure?
Nope.
Okay.
I apparently don't want anything but fill this out and really learn what the point is.
All right.
So, the procedure I gave you is written in the way a teacher would write the procedure to you guys, not the way you would put your procedure in a lab report. So if you were writing a procedure, which you are not, if my direction to you says measure the mass of 1 teaspoon of salt, what would you write down after you did it?
The mass of 1 tablespoon of salt was taken.
Measured,
Or
yes.
measured.
That would be good. And, yeah, you write exactly what you did. So if you accidentally measure, I overflowed the teaspoon and measured more than a teaspoon of salt, you write that, and then you record the mass in your data section. So always keep track of the stuff you do, if it's different, especially from what you were told to do. And that's just really critical, because then your teacher can find your mistakes, or if you discover something important, you can recreate that. Always write down what you did, not what you were told to do. Very important. But you're not doing that today. So we are going to keep track of 1 beaker for me, because we only have 1 burner. So I'll do the boiling part at the end. So I have a Sharpie somewhere. I will just Sharpie this beaker. This bag. There it is. Oh, I can mark it like this. I'm not going to get the outside wet. So here, this purple beaker is my beaker. One of y'all will use it, but we'll do it that way. So it says measure 1 teaspoon of salt. Look at the mass of that. And then mass of the beaker. Alright. Oh, the air current's not good.
You want me to turn off the fan?
It's okay, I'll go over here by Kristen, and then it won't get me, I think. Alright, here we go. Can you tear the scale, and then I'm not going to measure the weight of that either, so you can tear that out so we don't actually know the weight of it. Okay, so then take a spoon and measure a spoonful of salt there. Give it that's fine, a big bunch. You don't have to reclaim that, just measure what you get. Okay, so we've got 2.32 grams of salt. What did I say?
2.32.
Awesome, thanks guys. Here, I'll take that. Story of my life. Oh, good. Alright, I'm just going to throw it in here. Here we go. Squeaky speaker. Okay, now we're going to pass out oh no! Oh, I don't have enough funnels. Okay, we're going to do a demonstration today. I don't have enough funnels. Alright, so now we'll have you measure the mass of this beaker that I marked in purple. I only have 1 funnel. What was I thinking? Alright, so the salt was
13.26.
Okay, so we have our data. Now, we're going to look at this sand, which has in the past been used as a weight for physics experiments for 6 years, so hopefully not gross. Alright. If you do separating mixtures experiment in college like this, and you get to choose how much sand you use, what would be a sensible choice? Use a big bunch or use a small amount?
A big amount.
See, that's what I always thought too, but a small amount is always a better choice in the lab, because it's kind of a challenge to get the sand to come out of the mixture. Sometimes they're to come out of the beaker even. So we are not measuring the mass of the sand because we're qualitative with respect to sand and water. So pass this sand around and make some observations.
Should we write down the observations somewhere?
Well, let's talk about them. After everyone observes the sand, we'll think about what sand is. Jenny, hold the sand up to the camera too so it can be observed.
Okay.
And look at it yourself too.
I
You
have to like
millennials,
super.
don't watch your life through the lens of the camera.
I have to like super zoom in because it won't zoom in and can't focus on the sand.
Okay, now look with your own eye at the sand. Okay, now pass it on.
Just look like sand.
Like that.
Didn't say consider a homogeneous,
Well, once you observe it, then that's the next question in my mouth. But I don't want to ask it to have someone shout it out until all of y'all get a chance to look.
just to guess, right?
Wait till you see it, Michael.
I'm restraining myself from the questions. Okay, so now what do we think? What is this? Is it element, compound, heterogeneous, or homogeneous mixture?
Heterogeneous?
Okay, Kristen says heterogeneous. Anyone disagree? Okay, why do you say it's heterogeneous?
So like same and different.
Okay, well, contamination aside, does every actual sand particle look the same? No, we've got some real dark brown guys and some white guys and some big guys and some small guys. And I'm guessing that any sample piece that you took out would be different from any other sample piece you took. So, our observations here, which you can make a note of anywhere. Sand is a heterogeneous mixture. Now, I remember grading lab reports for this lab. Is that really true? I'm not feeling confident about my idea here. Hold on. That triggers a memory I have. Maybe I changed it because it's something 4.1, no report. Okay. Alright. So, on procedure and data number 1, make sure you write down the mass of the solid, and number 2, make sure you write down the mass of the beaker. Now we've observed our sand, and then, as long as the wind hasn't blown our salt away, I'm going to add all 2.32 grams of salt, carefully shaking every little bit off in.
If
So,
we put sand and salt to a 100 milliliter beaker, and we measured 250 milliliters.
that's what I have. So you can change your procedure because sometimes you just don't have what you want, including 4 funnels. So now I've added the salt in here. Now is it an element, a compound, a heterogeneous mixture, or a homogeneous mixture?
It'd be still heterogeneous, right? Because
Yep.
you haven't mixed it thoroughly yet.
Right, okay. Well, and the sand itself is heterogeneous, so there's
Right.
no way I could somehow turn this into sand plus salt is a heterogeneous mixture. Now, how about the salt all by itself?
Would that be considered a compound?
Yes. So how do you know?
Well, the chemical formula is NaCl, correct?
Exactly. So table salt like this
And the lighters.
is sodium chloride. Is it ionic or covalent?
It is. No, actually, it's ionic.
It's ionic because you've got a metal
sodium's a metal.
and a non-metal. So salt is an ionic compound. It's NaCl. It has a chemical formula. So if you were just observing our salt by itself, it would be a compound. How about our water?
Wouldn't that be also considered a compound?
Water is a compound. Ionic or covalent?
Covalent.
Water is covalent because it's H and O, which are both nonmetals. The reason I ask you, see it has a chemical formula, H2O. The reason I keep asking you ionic or covalent is I want you to train yourself to ask yourself every time you look at a compound's chemical formula. First thing you want is ionic or covalent because they behave very differently than you'll see later. And if you just immediately decide, then you're going to be in a good habit and you'll go the right path next. If you decide that quickly, you wouldn't just blindly follow one path that you prefer. You'll go the right way. Okay, so it says to start adding some distilled water, and then I'm going to filter the contents through the one and only funnel. Alright, so actually what I'm going to do here, I need this beaker. This is the beaker whose mass I have measured. So I'm actually going to do the filtering part into this beaker because then I'm going to keep using the purple beaker. So, I'm using a coffee filter as the filter. Here it is. And my goal here is going to be to separate the mixture of sand and salt. So, how would you think? There are a couple of ways that we could go about this. How could I separate a mixture of sand and salt? Alright, so salt.
When you pour water through it, which I assume you're going to do, it's going to dissolve the salt into it and bring it through the filter.
And what about the sand?
The sand would be too big to go. So
Okay, so salt dissolves in water, and its particles are so tiny that they go through the coffee filter. But sand, are its particles tiny? Not tiny enough to go through a coffee filter. And do its particles dissolve in water?
No.
No. So what we do here to separate this mixture is we consider its physical properties. So, let's see. This is kind of a key point. Now it doesn't matter if this mixture is heterogeneous or homogeneous. Okay, so we observed the sand, we observed the salt, and Saul told us that sand does not dissolve in water. Sand pieces are too large to pass through coffee filter. Okay. How about salt? What do we observe about the salt, and what do we know about salt?
It can dissolve.
Salt can dissolve in water. And will those dissolved pieces of salt in the water go through the coffee filter?
Yeah.
Yes. If I just put solid salt into the coffee filter, it wouldn't pass through. But when it's dissolved in water, it will. Okay, so I've got a heterogeneous mixture of sand and salt here. We've used the physical properties of sand and salt to decide that we can separate by dissolving one in water, the other doesn't dissolve, passing it through a filter, or one will pass through another one. Is there any other way we can separate this mixture, Liam?
You can comb through it with a fine comb.
Okay, that might get it mostly separated, and then You might have to go for tweezers. But, yep, if you had infinite patience, you could pick each particle apart, view it with your eye, say it is brown, it is sand, it is white, it is salt, and you might get it pretty well separated that way. So, another physical property we could consider is just sand is a different color than salt. Even though each piece is sort of a different shade, sand is brown, salt is white. We could just pick sand pieces out. We don't want to go that route because that would take all day, so we're going to go this other route. This is like full of nasty water, so I'm going to go for the clean one because I don't need to today. Alright, so this is a wash bottle. You'll find that in college, in the lab, you will, alright, so I'm going to add some water. Oof, that was way too much water. This will now take forever. Another thing, I said use a small amount of sand if given the choice. Use a small amount of water if given the choice because it takes forever. So I'm going to swirl it around to make sure my salt dissolves well. And I'll separate the mixture just like we talked about by pouring it through the filter and waiting, and waiting, and waiting. Let's see. Aim the camera, Jen. Hold. There we go. Aim. There we go. Okay, so when you can't get all the stuff out of your beaker, all you have to do is turn the beaker upside down, take your wash bottle, and everybody comes shooting right out happily. That was the technique you were going to practice today, but you're not now because I'm having a funnel. I don't know, I've never forgotten stuff for labs, and your class is like new disaster every day. Okay, so I got pretty well all the sand out of there. It passed through quickly, which